Hello guys, my name is Lazaro and today we're going to be doing a LeetCode problem. This problem is called minimum height trees. A tree is an undirected graph in which any two vertices are connected by exactly one path. In other words, any connected graph without simple cycles is a tree. Given a tree of n nodes labeled from 0 to n-1 and an array of n-1 edges, where edges of I is equal to a of I, b of I, indicates that there is an undirected edge between the two nodes a of I and b of I in the tree. You can choose any nodes of the tree as the root. So this last sentence pretty much is telling us that this graph is unrooted. Uh, we can start at any place. We don't have to specifically start at one node. Or we don't have to consider any one node as the root. When you select a node x as the root, the resulting tree has height h. Among all possible rooted trees, those with minimum height, min of h, are called minimum height trees. Return a list of all minimum height trees root labels. You can return the answer in any order. The height of a rooted tree is the number of edges on the longest downward path between the root and a leaf. So there's a lot of definitions here. The first paragraph is pretty much defining what an undirected graph is and what a tree is. Then the second paragraph is pretty much telling us our input, so what can we expect from this problem and what are we working with. And it's also defining what the problem is looking for. So it's looking for this minimum height trees. That might be something that we're unfamiliar with, so it goes ahead and defines it for us. And then finally the last two sentences, well, sorry, this second to last sentence, or I guess, I don't know, if you want to consider this paragraph, I guess you could, even though it's just one sentence. It's telling us what our output should be. So they want us to output a list of all minimum height trees. And this list should contain the root, where if we were to root the graph at this node, we will get a minimum height tree. And then the last sentence is yet again another definition, where it's defining what a height means. All right, so let's look at the first example. Right here, we have we're given that there's going to be 4 nodes in this graph, and we're also given the edges of these nodes. Now, so we can pretty much just say it looks like this, with 0 goes to 1, 1 goes to 2, and then 1 goes to 3. This is undirected, so 0 goes to 1 and 1 goes to 0, 1 goes to 2 and 2 goes to 3, 1 goes to 3 and 3 goes to 1. So what node should we choose where if we were to make that node the root, we would get a minimum height tree? If we were to choose 1, the height of this tree will be just 1, because the number of edges from the root to the lowest leaf is 1. If we were to make 2 the root, we will have a height of 2, because starting from 2 to the longest, or the leaf furthest down, we see 2 edges. And it'll be the exact same thing if we were to choose 3 or if we were to choose 0. Therefore, the only node that would give us the minimum height tree is 1. Now, this is not always the case. There might be 2 nodes that will give us a minimum height tree. In this example right here, in example 2, we have 6 nodes and 5 edges. But as you can see, if we were to choose 3 or 4, we will get the same minimum height tree. Therefore, our output should be 3 and 4 in an array. And the output would always either contain 1 node or 2 nodes. And I'll explain why. this is the case later on. But first off, let's just get into the drawing. And I do want to point something out, that this problem does deal with graph theory. So this is one of those problems where if you know graph theory and you have taken the class, for example, then you should be able to easily solve this question because you would know the trick. If you haven't, then you really have to just think about it a little bit, and it might take a while, but you should be able to eventually get it. So let's write down the first example. We have 0, 0 goes to 1, 1 to 2, and then 1 to 3. So keep in mind that this root, or this node that will give us a minimum height tree, is always going to be the center node. Now, why does this make sense? Well, if we choose the center node as the root, then the height, which is defined as the length from a node to a leaf node, or from a node to the lowest leaf node. That's what the height is. If we choose the center, then we're minimizing this path, because we're in exactly the middle of the graph. Therefore, any path from that middle node to a leaf, it would be the smallest. So if we were to look at this graph right here, the middle one is 1. And that is also the correct answer. Now let's say here we have 4 nodes and 4 is even. Let's say we had an odd amount of nodes. Let's say 2 goes to 4 right here. Now what would be the answer? Well, if 0 was the root, we would be seeing 1, 2, and 3 edges, because that's the lowest leaf. 4 is the lowest leaf. So far we have a height of 3. If we were to make 3 the root, we would see 1, 2, and 3 as well. Okay, that's the same as 0. If we were to make 1 the root, we would see 1 and 2 edges. If we were to make 2 the root, we would see 2 edges as well. Will be 1 and 2 there and 2 here as well. And if we were to make 4 the root, we would see 3. Therefore, the minimum height would be 2, and that's if we choose 1 as the root or 2 as the root. Now, these 2 nodes, they can be considered as the center. Now, why is that? Well, because technically the center is right in between them. So right in between this edge. But since there's no node there, the center is broken up between these 2 nodes. It's broken up and shared between node 1 and node 2. And this is why I said that the output would always be an array of size 1 or an array of size 2. It would either contain 1 node or 2 nodes. So now with this information, we know that all we have to do is just find the center. So now we have another problem on our hands. How could we find the center? And to do this, all we have to do is delete the leaf nodes one by one until we are left with either 2 or 1 nodes. If we look at this problem right here, if we delete all the leaf nodes, we are left with 2 nodes. And that's when we know to stop. As long as there's more than 2 nodes in our graph, we know that we have not been left with only the center nodes. So there are some more nodes that we can delete. And so let's continuously be deleting the leaves until we are only left with 2 nodes. Now let's do a separate example. Let's say 3 had 5, 0 had 6, 1 had 7. Let's implement this algorithm we talked about. Let's delete all the leaf nodes in this round. So it's 4, 5, 6, and 7. How many nodes are we left with? We're left with 4. 4 is greater than 2. So now we rerun it. The new leaf nodes will be 2, 3, and 0 now. Because remember, we deleted their children. So now let's delete this new leaf nodes. So we remove 2, remove 3, and remove 0. How many nodes are we left with? We're only left with 1, and that is less than 2. So we stop and we know that this is our center, or this is the node that we should root this tree at. And this is true because let me switch back to black. The path to the lowest leaf is 2 everywhere. The center is no longer 1 and 2 because if we were to root it at 2, we can see a path of 3, or we can see a height of 3. Perfect. So now we know the trick to solving this problem. Let's actually get right to it. Let's write the code for it. Alright, so the first thing I'm going to do is import a dequeue from collections. The reason I'm doing this is just so I can append on the left side or append at the end of a list. Just be helpful later on, as you guys will see. First, let's just take care of a simple edge case, and that's if n is equal to 1. If that's the case, then we know we just want to return 0. If there's only one node and the nodes are labeled from 0 to n minus 1, then we just have to return 0 because that's obviously the root node, or the node that we should root this graph at. Next, we want to build out our matrix. I'm going to be setting this as a hash map, and it's going to represent a adjacency list where for every node u in the range of n, and now this range will give everything from 0 to n minus 1 because it excludes n. I want to add this node to my matrix, and I want to have it and I want to give it a value of an empty set. The reason I'm doing an empty set is just so I can add and remove nodes from this adjacency list in all one time. Now we can iterate over our edges. So for u, v, and edges, we want to add it to our matrix or to our adjacency list, where u can go to v, and since this is undirected, v can also go to u. Now we want to initialize our leaves, and initially it's an empty array. But let's just go over our matrix, which we can just do similar that's how we started here. So for u in range of n, if the number of adjacent nodes for this current node is equal to 1, then we know it's a leaf. The reason I'm doing equal to 1 rather than equal to 0 because remember this is undirected. So 3 will have an edge to 1. So for it to be a leaf, it needs exactly 1 edges, or 1 other node that it can go to. Now if it meets this criteria, then we know it is a leaf, and let's add it. So those are our initial leaves, and now what we want to do is, well, n minus the length of the nodes we have removed, which we can initialize as an empty set. While this is greater than 2, we want to remove the leaves. So what exactly is this saying? Well, this is saying for the total amount of nodes we started with minus the number of nodes we've removed. If that's greater than 2, then we have not yet seen our center nodes or the nodes we should root this graph at. Now let's get the number of leaves, which is just the length of our leaves array. And while this number is greater than 0, we know we want to remove this leaves and also remove it from its parent nodes. So let's get the current leaf we're looking at. We can just do that by calling the pop function. And let's get its neighbor node. So we can just look at the adjacent nodes for this current leaf. And let's pop it from there. So we can set this set to be an empty set. Now something else we want to do is actually remove this leaf from its neighbor node as well, from the neighbor node as well. So matrix of V, let's remove the leaf. Now, if the length of this adjacent node is equal to 1, then we know that this parent node is now a child. Or this parent node, after removing this leaf, has turned into a child. Now, a simple example of that is this 3 right here with the 5. When we remove the 5, 3 only had one adjacent node, which was 1. So the parent of 5 became a leaf when we removed 5. And since this 3 became a leaf, we want to add it to our leaves array. So let's just append left v. The reason I'm doing append left is because in the next iteration, since I'm popping from the end of the array, I do not want to mistakenly take the current node I just added. So this is the reason I'm using a dequeue. Append left is O of 1 time. So it's just, it helps bring down that time complexity. I could have also just created a new leaves array out here outside and then just add it to this, but I decided against that. And then finally, we want to add this leaf node to our removed set, which represents all the nodes we have removed from our graph. And of course, the number of leaves we want to decrement as well. So after running through all of this, we should have been left with just 1 or 2 nodes in our matrix, or in our graph, since a matrix represents our graph. So we can set answer equal to an empty array. And now for u in range of n, if u is not in our removed set, then we know it's one of those center nodes. So let's append it. And then finally, let's return the answer. So let's run the code, see if I made any mistakes anywhere. Okay, let's run some more test cases. All right, perfect. So before I submit, I do want to discuss what exactly is going on. First, in the first line of this method, we're just doing a simple check. If n is equal to 1, then we know exactly what we have to return. So let's just go ahead and return it without doing any of this computation. If that's not the case, then let's build out our matrix. In this case, I'm using an adjacency list. That is the data structure I'm going to be using to represent this graph. After building out this matrix for all of the n nodes, which is labeled from 0 to n minus 1, let's look at the edges. And now let's add the edges to our adjacency list. So we know what node goes to another node. Finally, I start off by first getting my initial number of leaves, my initial set of leaves. I can do this by just going over my adjacency list. If the neighboring nodes of this current node I'm looking at is just one, then we know we're on a leaf, or this current node is a leaf, because since this is undirected, if it only has one edge, then we know it's a leaf. And then finally, what I'm doing in this lines 20 to 32, I'm removing all the leaves until I am left with 2 or 1 nodes in my graph. I'm also keeping track of what nodes I removed by having a removed set that represents all the nodes I have taken out. And then finally, I want to go over all the nodes from 0 to n minus 1. And if a node is not in my removed set, I know that node is a center node, or is a node that we should root this graph at. And then we return it. So now let's submit, and it works perfect. So this was a pretty interesting problem. You guys did have to know a little bit of graph theory uh, to see how this works, or see how this maps out. But hopefully you guys were able to see it with this video. So like always, if you guys enjoyed, please leave a like and consider subscribing. And thank you very much for watching.